Before we can do calculus in many variables, we have to learn about the Euclidean space Rn. That's the space in which we're going to work. So in this lecture, we're going to learn some basic facts about Rn. We're going to cover the definitions and basic binary operations on Rn. And we're going to consider all dimensions, not just 1, 2, and 3, but 4, 5, 6, and so on. We're also going to explain how the geometry of Rn can be discovered from its natural inner product or dot product. It turns out that the dot product gives a lot of geometric information about Rn. And we're going to prove the Cauchy-Schwarz inequality. In fact, we're going to prove it twice. All right, let's get into it. Let's talk about n-dimensional Euclidean space Rn. When we talk about Rn, we can mean various things. First of all, Rn is a set. It's a collection of objects called points or vectors. So at a basic level, it's just a set. But Rn is also a linear vector space. It has a linear structure. This means that you can take 2 points in Rn, or 2 vectors of Rn, and add them together and get another vector. And you can multiply vectors by scalar numbers, by real numbers, to increase their length or to multiply their lengths by a positive or negative factor. So these two operations are called vector addition and scalar multiplication. Lastly, Rn has a geometric structure. Not only can we add vectors and multiply them, but vectors have a length, and we can also measure angles in Rn. So this gives us some geometry to work with. We can talk about angles, and we can talk about distances. This is not a property that all vector spaces have. This is a property that vector spaces with an additional inner product structure have, or inner product spaces. So Rn is a set, it's a vector space, and it's an inner product space. And we're going to discuss in more detail each of these 3 properties and give precise definitions. Okay, at a basic level, Rn is a set. What is a set? Well, you'll recall that a set is a collection of objects called elements. Okay, so that's a fairly basic notion in mathematics. What is Rn as a set? Well, it's the set of n tuples, that means in-ordered real numbers, x1 through xn. If we change the order of the xi's, then we have a different point of Rn. So we say that Rn is the set of ordered n-tuples of real numbers. You're, of course, already familiar with R1, the case n equals 1. That's just the set of real numbers, because a list of only one number is just the same as the set of numbers. You're probably also familiar with R2. That's the 2-dimensional Euclidean space, which is identified with a plane, and R3, which is 3-dimensional Euclidean space, which we think of as the kind of space that we occupy in 3-dimensional. In other words, we can visualize 1-dimensional Euclidean space, the set of real numbers, as a number line. In the case n equals 2, we can visualize R2, the 2-dimensional Euclidean space, as being the plane, where every point, P, every dot on the plane, can be identified by its x and y coordinate. In 3-dimensional Euclidean space, of course, we try to draw a picture of like this, with the z-axis going up, the x-axis, the y-axis to the right, and the x-axis kind of coming out of the board. And every point P can be identified with its x, y, and z coordinates. So in this way, the set Rn can be visualized like this, at least in dimensions 1, 2, and 3. Okay, let's discuss the vector space structure of Rn now. We call elements of Rn points or vectors. I've already sort of been doing this, depending on what's appropriate, kind of according to the picture we have in our head. But this is mathematically equivalent. Points and vectors of Rn, they mean the same thing. A point we just think of in pictures as being kind of a dot sticking in the plane, for example, in R2. Whereas the same point P, if we wanted to picture it as a vector, we'd have an arrow coming out of the origin ending at P. So we think of vectors as kind of arrows with a starting point going to an ending point. And this is really just a difference in how we imagine it. But these two pictures are equivalent. Okay, but let's talk about vector addition now. How do we add vectors? What does it mean to add vectors? Okay, well, vector addition, if you have 2 points or 2 vectors, then you just add up their coordinates to make a new vector. In pictures, this has a nice representation. So if we have 2 points P and Q, say in the plane, we can draw their vectors. And the way that we find P plus Q is we kind of translate the vector Q up so that its arrow begins at the tip of P, represented by this purple arrow. And then we draw the red arrow starting from where P started from and ending where the purple arrow is. And that red arrow represents P plus Q. So in terms of the actual definitions, if P is given by x1 through xn and Q is given by y1 through yn, then P plus Q is just the vector that's coordinates are x1 plus y1 ... xn plus yn. Okay, let's talk about scalar multiplication now. For scalar multiplication, we have a vector P, say this one over here, and we have a real number, say alpha. Okay, and say if alpha is 2 or alpha is minus P, what it means is that you keep the direction of the vector the same, and respecting minus signs, and you scale it by the amount of the real number. So in terms of equations, if you have P, x1 through xn, and a real number alpha, you just find alpha P by multiplying each of the coordinates by alpha. Okay, something that should be emphasized about this notion of vector addition and scalar multiplication is that they play nicely together. And they play nicely with the usual addition and multiplication of real numbers. So for example, if you do alpha P plus alpha Q, you get alpha times P plus Q. Notice that the plus on the right is vector addition, the plus on the left is vector addition, and scalar multiplication in all 3 places. Okay. Similarly, if you do alpha times P plus beta times P, it equals alpha plus beta times P. On the left, the notion of plus is vector addition. Scalar multiplication is happening in all 3 places. But the plus on the right is actually the addition in the usual sense of real numbers. So here we have 3 different sort of binary operations that are all playing nicely together. Okay, so there's other properties as well, like for example, scalar multiplication plays nicely with the multiplication of real numbers, like this associativity property, and so on. And this makes Rn into a vector space. Okay, let's discuss how to find the equation of a line in parametric form between 2 given points. Suppose P and Q are in Rn, and P is not equal to Q. So we have a point P over here and a point Q over here. The vector from P to Q, which we denote pictorially as the arrow from P to Q, it has coordinates Q minus P. So it's just you just imagine P's at the origin and the vector goes from P to Q. So if we start at P and then add Q minus P, we get Q. So that's the point, is the vector is from P to Q is the thing that you need to add to P to get to Q. So it's Q minus P. Okay. So let's draw a picture and a vector from P to Q. And let's draw Q minus P below. Notice that I mislabeled that and wrote P minus Q, but it's really Q minus P at the bottom. Well, if you look at the set of all multiples of Q minus P, then it's the purple line that I'm drawing here at the bottom through the origin. So now we know how to draw the equation of a line through the origin. If we add P, though, to the purple line, we get the line passing through P with the same slope, because it's just going to be a translation. And this leads to the line in red, which is exactly the line that we wanted to find the equation of. Okay, let's summarize this. To find an equation of a line in parametric form between 2 given points, P and Q, we first find the vector Q minus P. If we look at all scalar multiples of that vector Q minus P, then we get this purple line here. Okay, if we translate the purple line by p, that is add p to this set, so look at the set of all points p plus scalar multiples of q minus p, then we get this red line, which is exactly the line that we wanted to find. So the red line is the set of all points that have the form p plus t times q minus p over all real numbers t. And you can rewrite this if you pull this part out front and write the p's together. Then you can write it as t times q for this factor and 1 minus t times p for this and this. Of course, this is not the only way that you could write it. For example, you could write it as the set of all tp plus 1 minus tq, such that t is a real number. Okay, let's see an example. Find the line passing through the point 1, minus 1, 6, and minus 2, minus 2, 4. Okay, so let's compute the direction of the line. So we're going to let, let's say, v be the vector minus 2, 4, minus 1, 6. So I did the second vector minus the first vector. Of course, you can do the first vector minus the second vector. You'll just get a different parametrization. So what is v in this case? Let's see if I can do it correctly. Minus 3, minus 1, minus 2. So that's the direction of v. Okay, and so then the line is the set. Okay, so now if I chose the vector that went from this point to this point. Since I did that, I have to make the line be anchored at the first point. So the line is the set 1, minus 1, 6 plus t times minus 3, minus 1, minus 2, such that t is a real number. Okay, another way to write this is to say the line is the set of all x, y, z, such that x equals 1 minus 3t, y equals negative 1 minus t, and z equals 6 minus 2t, where t is a real number. And this is called a parametrization of this line. Parametrization of the line. Okay, now I'd like to talk about this notion of parametrization by thinking about more general curves. In fact, a curve is defined to be a function, say phi, from an interval I of the real numbers into Rn. So again, I is just some interval. It could be all of Rn, or sorry, all of R, for example, but it doesn't have to be. It can just be some finite interval. Okay, so we typically think about curves as kind of looking like this. And here, this is just the image of our phi. So our phi is taking points in the interval and spitting out points on this curve. So if you take two different inputs, t and s, you'll get two different outputs. And as you kind of wiggle the input parameter, you trace out this curve. As you slowly vary it, you end up tracing the curve. We have to distinguish the difference between the curve as a function phi and the image of phi. And this kind of gets to this idea I said earlier about how you can have two different parameterizations of a line. Basically, this curve here, the image of it is unique. But we could have different parameterizations, different functions phi, whose image is that curve. You can imagine if phi of t represents the position of a bug, okay, in space, and the bug is moving along this curve, it could move along the curve at different speeds. You know, for instance, it could move at a constant speed. It could move at a faster constant speed. It could even, start off fast, backtrack a little bit, have negative velocity, and then turn back around and go in the other direction. And each of those different kind of functions phi, which describe the position of the bug at time t, will correspond to different parameterizations. Okay, now I want to turn to the next topic of the geometry of Euclidean space. So where does the geometry of Euclidean space come from? Well, it comes from the inner product, the natural inner product on Euclidean space. Now, the inner product you're probably already familiar with. It's also called the dot product. To define it, you just got to take the product of the coordinates and sum them up. Okay, so let's define it carefully. Suppose we have two vectors, x and y, and let's say that the coordinates of x are x1 through xn, and the coordinates of y are y1 through yn. Okay, the dot product of x and y, which we denote by x dot y, is defined as follows. Just you do x1 times y1 plus x2 times y2 plus, and you keep going until you get to the end, xn times yn. You can write this symbolically more compactly with some notation like this, xi, yi, sum over I. Okay, now it's kind of surprising, but this binary operation, this very simple binary operation, which you're probably already familiar with, actually encodes a lot of geometric information about n-dimensional Euclidean space. This is because the dot product allows you to define a notion of distance and a notion of the angle between two vectors. And if you can talk about distances and you can talk about angles, then you can really talk about geometry. Okay, let's talk about how the dot product allows you to define distances in Rn. As you probably know, if you have a vector x in Rn with coordinates x1 through xn, then you can define the length of this vector by taking the dot product of x with itself and taking the square root. This is exactly the Euclidean distance. It's the square root of the sum of the squares of the coordinates of x. Okay? So the dot product gives you a notion of distance. I'm writing the length of x with only one bar. Sometimes it's written with 2 bars. All right, so now if we have 2 points, say P and Q, how do we define the distance between P and Q? Well, the distance between P and Q is just the Euclidean length of the vector from P to Q. That is, it's just the length of Q minus P. And since the Euclidean distance is the same for x and minus x, of course, the distance from P to Q is the same as the distance from Q to P, as you would expect. Let's discuss how the dot product gives us information about angles. In order to do that, I'm going to back up a little bit and talk about the bilinear structure of the dot product. By bilinear structure, what I mean is that the dot product has the symmetry and sort of associativity properties that you'd expect. So if you multiply x dot y by alpha, it's the same as multiplying x by alpha and then dotting it into y. If you do x plus y dot z, it's the same as doing x dot z plus y dot z. And that's true for all x, y, and z in Rn and all scalars alpha. Of course, the dot product by definition is also symmetric. X dot y is y dot x. Okay, so let's talk about how we can see from the dot product when 2 vectors are perpendicular, that is, when the angle between them is 90 degrees. For this, we're going to use the Pythagorean theorem. So the Pythagorean theorem says that 2 vectors are orthogonal if and only if the length of the sum of the vectors squared is equal to the sum of the squares of their lengths. So if x is perpendicular to y, then x plus y squared is the length of x squared plus the length of y squared. So let's write that down in terms of dot products. So x plus y length of it squared is just x plus y dot x plus y. And that is the length of x squared plus the length of y squared plus 2x dot y. And that comes from the rules in part 1 above. Meanwhile, x squared plus y squared is x dot x plus y dot y. And you see that these two things are equal if and only if 2x dot y is 0, that is, x dot y is 0. So x dot y is 0 if and only if x is perpendicular to y, and that's true by the Pythagorean theorem. So you see these two numbers have to be equal, and that means that x dot y has to be 0. Let's talk about how to compute the projection of one vector along another vector. So if I'm given two vectors, x and y, I'd like to compute this red vector, p, which is the projection of y along x. You can see from the picture what I mean. This allows us to write y as the sum p plus y minus p. And y minus p is this vertical vector here, which you can see is orthogonal to x. So that's what characterizes the projection p. P is the vector p, so that when you write y as p plus y minus p is orthogonal to x, which means that y minus p dot x is 0. So that allows us to compute y dot x in terms of p, because y dot x is just p dot x. Therefore, if p is alpha x, like it looks like in the picture, then p dot x equals alpha x dot x, and that's alpha times the length of x squared. Now we can solve for alpha. Alpha is just p dot x divided by x squared, which is, using the formula above, we substitute, is just y dot x divided by x squared. And therefore, p is just alpha times x, and that gives us a formula for p, y dot x divided by the length of x squared times x. And this is the formula for the projection of y along x. Now that we have a formula for the projection of one vector along another, we can compute the angle between them. So let's look again at our picture. We have a vector x and a vector y. We have a vector p, which is the projection of y along x. And we have this vector y minus p, which is orthogonal to x. Now we have a right triangle, because p and y minus p are orthogonal, and that allows us to compute the angle theta as the inverse cosine of the length of p divided by the length of y. We have a formula for the length of p in terms of x dot y. P is just x dot y divided by length of x squared times x. And so the length of p is just y dot x divided by x. Therefore, theta is the inverse cosine, substituting that value for p in, we get y dot x divided by the length of y times the length of x. And this is a formula for the angle between two vectors just in terms of the dot product, because everything on the right-hand side is defined in terms of dot products. Okay, next I'm going to discuss two important inequalities. The first is the Cauchy-Schwarz inequality. Okay, what does the Cauchy-Schwarz inequality say? The statement says that for every pair of vectors x and y in Rn, if you look at x dot y and take the absolute value, it's at most the length of x times the length of y. Okay, let's see the proof of that. Well, we actually basically already proved it, because we already proved that x dot y, an absolute value, is the length of x times the length of y times cosine of theta. I should maybe start the proof by saying for every x and y in our n, we have that the absolute value of x dot y is the length of x times the length of y times the absolute value of cosine theta, where theta is the angle between x and y. Okay, so now to finish the proof, you just have to notice that this cosine here is at most 1. And that's the end of the proof. All right, let's look at the second inequality, which is called the triangle inequality. The triangle inequality says that for every pair of vectors x and y in Rn, the length of x plus y is at most the length of x plus the length of y. Now the proof of this basically boils down to Cauchy-Schwarz, so let's see it. First I'll draw a picture so that you can see why this is called the triangle inequality. Okay, proof. We just do a calculation. So we compute the length of x plus y squared in terms of the dot product is x plus y dot x plus y. And that's equal to, using the distributive properties of the dot product, it's the length of x squared plus the length of y squared plus 2x dot y. And now we just use Cauchy-Schwarz on the third term. And we replace x dot y by length of x, length of y. And now we collect terms. And notice that the whole expression is equal to the square of the length of x plus the length of y. If we take the square root of both sides, we have the triangle inequality. So that's the end of the proof. The Cauchy-Schwarz inequality is very important, and therefore I want to give you a second proof. So this proof is going to be a little bit trickier. We're going to assume that x is not 0 and y is not 0. Now that's okay, because if one of them is 0, then the inequality is trivially true. Now I'm going to take a real number t, and I'm just going to compute x minus t times y dot x minus t times y. This is bigger than 0, obviously. Therefore, 0 is less than length of x squared plus t squared length of y squared minus 2t x dot y. Now let's put x dot y on the other side and divide by 2t. X dot y is less than 1 divided by 2t, x squared, plus t divided by 2, y squared. Here I guess I'm assuming t is not 0, but that's okay because I'm about to choose t and you'll see that it's not 0. Now we're going to make a clever choice of t. Really, we should choose t to minimize the right-hand side of that expression because there's t's on the right and no t's on the left. I want to make the inequality as good as I possibly can. So we're going to minimize the right-hand side with respect to t. You know how to minimize expressions. You just compute the derivative in t and set it equal to 0. And when you do that, you get that t should be the length of x divided by the length of y. So when we substitute that in, you see that the two terms in the sum are equal. They're both 1/2 the length of x times the length of y. So we end up with x dot y is less than half the length of x times the length of y, plus another half of the length of x times the length of y. And that's what we wanted to show. We're not quite done because we needed to have the absolute value of x dot y. But if we run the argument that we just gave with minus y in place of y, then we get also that minus x dot y is less than length of x times length of y. And putting those two together, that gives us that the absolute value of x dot y is less than the length of x times the length of y. And that's the end of the proof. Okay, let me explain why I showed you a second proof of Cauchy-Schwarz. There are 4 main reasons why the second proof is better. The first is that it works in more general inner product spaces. We don't need the Pythagorean theorem to make it work. So the second proof does not require any prior knowledge. We didn't have to know about cosine, and we didn't have to know about the Pythagorean theorem. The third reason is that it's purely algebraic. This is both kind of a blessing and a curse. The sort of more geometric proof may have been more intuitive, but the more algebraic proof is also nice because it allows us to run the proof without ever having to draw pictures or think too hard. It's just purely algebra. It also introduces you to a new trick for proving inequalities that will come in useful time and time again. You introduce a new parameter, which was the t. You do some smart calculation involving t, and then you minimize what you get. You optimize it over the parameter t. This is a trick that will come in handy very, very often. Let's do some examples. In the first one, I want to compute the projection of this vector in R4, 2, 4, minus 1, 2, along this other vector in R4, 1, 0, minus 1, 2. Okay, so how do we do it? Well, let's just apply the formula. We're going to let P be the projection. And remember that this notion of projection is not symmetric. If you compute the projection of the second one along the first, you'll get a different answer than the projection of the first along the second. So I'm going to name the first one y and the second one x. Okay, now my answer ought to be something that is in the same direction as x. Remember, the formula is y dot x divided by length of x squared times the vector x. All right, so what is that? Well, we have to do y dot x, so we multiply their coordinates and we sum. Let's write it all down just to be careful. So we have 2, 4, minus 1, 2, dot 1, 0, minus 1, 2, divided by, well, 1, 0, minus 1, 2, dot 1, 0, minus 1, 2. And all of that times x. 1, 0, minus 1, 2. Okay, so we just have to compute the numerator and denominator. So it's, for the numerator, I get 2, and then I get 0, and then plus 1, and then plus 4. And in the denominator, I get 1 plus 0 plus 1 plus 4. So when I simplify that, I get 7 over 6 times the vector. Now I forgot to write the vector in the first equal sign on the last line. But what you get is 7/6, 0, minus 7/6, and then 7/3. And that's it. All right, let's see another example. In this example, I'm going to find the set of vectors in R3 which are orthogonal to both 2, 1, 0 and minus 1, 0, 1. All right, so let's think about what it means to be orthogonal. The vector x, y, z is perpendicular to v and w, where I'm going to call these two vectors v and w. It's orthogonal to v and w if and only if the dot product with each one is 0. So that means that 2x plus y is 0, and it means that minus x plus z is 0. Okay, because the first one is v dot xyz, and the second one is w dot xyz. Okay, let's erase that. All right, so let me rearrange these. This is a pretty easy system to solve. It just means that x equals z, I guess. That's what the second equation says. And the first equation says that just x is y over 2, or minus 1/2 y, I guess. All right, so this says that xyz must be x, and then minus 2x for y, and then x again for z. So you have to have that form, x minus 2x, x, and you'll be orthogonal to both vectors. Therefore, the set we're looking for, I can write like this. I can write it as the set of all scalar multiples of the vector 1, minus 2, 1. So the set of all t times 1, minus 2, 1, where t is a real number. You can notice that this is actually a line passing through the origin. Okay, so this is the end of this video. Let's have a review of what we learned. We learned that Rn is a set, but it's more than that. It's also a set with a vector space structure. This means there's a notion of addition for vectors and multiplying vectors by scalars. And those two notions play well together and have nice associative and distributive properties. That makes Rn a vector space. Rn is also equipped with an inner product, or dot product, and this gives it a geometric structure. The dot product allows us to compute the lengths of vectors as well as the angle between two vectors. And we also learned the Cauchy-Schwarz inequality and the triangle inequalities. The triangle inequality is an easy consequence of the Cauchy-Schwarz inequality. And the Cauchy-Schwarz inequality is a very important inequality involving the inner product.